Grothendieck school of thoughts. This is the fourth lecture on the lower algebraic K theory of rings by Professor Amit Kuber, and it's the last lecture of this section. In this lecture, we are going to see the notion of negative K theory and K2 of rings. So please start.
Thanks a lot. Thanks, Mainak. So recall that so far we have in 3 lectures, we have seen what is K0 of a ring and K1 of a ring. And K0 measures the spread of this category of projective modules, finitely generated projective modules, whereas K1 measures the eventual automorphism group up to abelianization. And we have also seen the notion of K0 and K1 of a symmetric monoidal category as well. And ultimately, like the last result that we saw was this 6-term long exact sequence consisting of rings and like K0 and K1 of rings, quotient rings, and relative K groups. So today, our goal is to extend this sequence to the right to infinity and to the left with 2-3 more terms. So we'll first start with K2 and we'll see some theorems for lower K theory, which will motivate the definition of negative K groups. And then finally, we'll end today's lecture with fundamental theorem of algebraic K theory. So any questions from previous lectures? Okay. If there are no questions, let us start directly. So this K2 of R has its origins in something very different. It's an independent topic. Devajyoti, Fatima, if you have any questions. Yeah, otherwise please mute. Yes, thanks. So I'm saying, so K2 of R has its origin in study of groups. Yeah, so it's part of group theory, an independent part of group theory, where we are trying to study. Yeah, so we're trying to study something called universal central extensions. So let me quickly explain what is universal central extension. So an extension of a group, this is same thing as we do in abelian categories. So an extension of a group G by a group A is an SES, yeah, short exact sequence of this form. What do? We start with 1A and, well, G and 1. So this group need not be abelian, so that's why I'm writing it multiplicatively using ones. Yeah, so the trivial group is 1. Yeah, again, I mean, same request as always. If somebody doesn't mind, then they can switch on their videos. I would like to talk to people and see their reactions. Yes, thanks. So you put an X in between. So if you can put this, then this is called an extension. So such an extension is central. Yeah, so X is a central extension. I mean, usually we also care about this map. So X comma phi is a central extension if A is contained inside the center of the group G, X. So that's why it's a central extension. Now, as the name suggests, universal central extension would be the universal one amongst all such extensions. So basically, we can define maps between central extensions as simple thing. So 1 A1 X1 phi1 G1 and 1 A2 X2 G1, and these two are equal and these maps have to commute. Okay, so these are maps between central extensions. You can define equivalence relations and so on, and there is some very nice relationship with cohomology of a group, but we are not going to go into those details. But universal central extension is the initial object in this category. So universal central extension is the initial object in this category of central extensions of this group. Now, one simple question we can ask: when does this universal central extension exist? So this is a theorem. So the theorem says that, so I'm just going to write UCE of G exists if and only if G is perfect. Now, perhaps somebody can tell me from last lecture, what perfect group did we see last time? Does anybody remember that? Do you remember what perfect is? At least give me a definition.
Special linear groups?
Commutator is same as the group.
Yes, commutator is same as groups. Yeah, I mean G is equal to. Yes. So have you seen an example of a perfect group while studying K1?
Special linear groups?
For K1, no.
Elementary group.
Elementary group, exactly. Infinitary elementary group. That was perfect group. Yeah, so that is how we are going to motivate this. So you see a universal central extension of G exists if and only if G is perfect. Moreover, I mean, whenever this happens, whenever G is perfect, then X is perfect. X is perfect, and phi is simply projection. Phi is the projection map. So basically, I'm telling you that you will have some A, then you will have G cross A, and then you will have G. And this will be the first projection map. So whenever universal central extension exists, then it has to be of this form. So this is a theorem in group theory, and therefore, obviously, because we know that there is one spatial group which is perfect, which is ER. So we are going to study the universal central extension of ER. So before that, I mean, we can also say, so if G is perfect, then and one RFG1 is a presentation for G. So what is the meaning of presentation? That this is a free group, free abelian group, free group, and this is the group of relations. So generators and relations. Then what is the universal central extension? Then 1 H2GZ. So this is the homology group, H2GZ. Then FF modulo. Yes, somebody wants to say something, Naba or Rijul? to G to 1 is UCE. So this result is also the one particular form of what it should look like. Okay, so the commutator of F quotiented out by the commutator between elements of R and F. So this will be the universal central extension. Well, still we haven't really clarified what we really mean, like what is its connection with K theory. So the K group, so it define K2 of R as the kernel of, so we need the universal central extension of ER. So let's say UCE of ER, we haven't yet specified what it is, to ER. Okay, so this is the map phi that we have been talking about. So it is simply the kernel of this map. Right. So far, like nothing is clear as such, but will, yes, Avadh Bihari, yes. Do you have a question?
दे जा सकता है, दिक्कत नहीं। तो आपकी हैंडराइटिंग तो टाइप के बराबर ही है, ठीक है, फिर वो हैंडराइटिंग उसको आप जैसे अलग अलग है ना, बाइनरी टाइप से।
Okay, fine. So let us define K2 of, yeah, so K2 of R is this kernel. Now, do you remember how ER was defined? ER was defined as the group of elementary matrices. And those elementary matrices were generated as a group by EIJA. Yes. So we are going to do something similar. And this is where Steinberg's name comes into picture. So Steinberg groups. So these are defined as ST and R. So we have to take some elements, choose some elements from R, and N is also important. It generated by symbols. Yeah, I mean this set Xij A, where 1 is less equal I not equal to J less equal N, and A is in R. So we'll have similar kinds of generators, modulo relations given by. So these are the relations that Xij, I mean, these relations are exactly the same relations that we wrote last time. But the only difference here is that we are not talking about Xij as certain matrices, as elementary matrices. We are just talking about these relations, abstract generators and these relations. So Xij R, XKLS. I mean, this is perhaps a shorter form of writing these, so that's why I'm repeating them. So 1, if J is not equal to K and I is not equal to L, then it is XIL RS. If J is equal to K but I is not equal to L, and XKJ minus SR if J is not equal to K and I is equal to L. So these are the generators. And with these generators, now naturally we have a map from not STNR to ENR, where you send a generator Xija to EIJA. So that's a natural surjective map. The relations are exactly identical. And then K2R will be the generator. K2R will be the kernel of this map, provided, I mean, further defined STR as the direct limit. So limit as n is in n of STNR. Okay, so by doing this, we get this particular presentation: 1 K2R STR ER1. So this is an exact sequence. Yeah, where this is the natural projection map that you can think of. Xij A mapping to Eij A. So in STR, the Xij's don't have any meaning. They are not necessarily matrices, but in E, when you map them to ER, they are matrices. In fact, we know something more. So in fact, like you just need enough room to move around. So STNR is the universal central extension of ENR for n bigger equal 5. Up to n is equal to 4, 1, 2, 3, 4, we can't really say anything. But eventually this starts happening, and therefore then you can conclude that STR is also the universal central extension of ER. All right, so Steinberg, so this particular short exact sequence is due to Steinberg. Furthermore, Curver and Steinberg proved this other result, which I already kind of stated. So they showed that K2 of R is also the, sorry, I shouldn't say definition, we have already defined it. It is isomorphic to the second homology group of ER. So you remember what happened earlier. Yeah, I mean, just recall quickly that K1R was isomorphic to H1 of GLR. Right. So now, yeah, sorry, this is AK1. I should change this. So you can see the pattern. Yeah, K1 of R is H1 GLR. Then we take its commutators group, and then we do this. So basically, all K1, K2, and so on, they are going to be abelian invariants of eventual spread, like, yeah, sorry, eventuality of this category of projective modules. In fact, I think we also have the result that K3 of R is the third homology group of ST of R. However, these things are really hard to calculate. And as we saw last time, that Bass would talk about symmetric monadal groupoids again. And K2 of R can also be written as the direct limit as P is in Projar of H2 of the commutator groups of automorphisms of P, automorphism group of P, Z. So again, recall that K1 of R was isomorphic to the same kind of limit with H1 of aut P and Z. Of course, for both these things, we have to assume that translations are faithful. Okay. So any questions so far? Okay. So the first two homology groups of ER actually turn out to be 0. That was also shown. Of STR, they turn out to be 0. Now, the usual things whenever we define,
sir?
Yes.
Can you explain this last line, K2R being this H2R? I don't know how this came from.
Oh no, I mean, this is a result from Bass. Yeah, I'm not giving you any proofs. This is a study of K2 is really hard. So this is simply the commutator group. So what we did for K1, we made this projective module large and large. And because translations were faithful, so automorphisms of P would embed inside automorphisms of P direct sum Q. Now for K2, we are doing something more complicated. We are taking the commutator subgroup of the automorphism groups. Then we are computing the direct limit of its second homology group. And I just wanted to show that these two have similar nature. Similar kinds of definition. Yeah.
Okay, so you wrote recall K2R, so I was confused. Did we see this last?
No. This recall is for this. Recall is for this line, and recall is also for K1R. This was for K1R.
Okay, that's
this
K1R.
is for K2R. Yeah, this is K1R. Okay. Yeah, I wanted to compare. Sorry. So if you put this direct limit inside, then automorphism of P will become GLR. So GLR, so that is ER. So this group will become ER, and that is precisely what you have here. So I'm just giving you that for symmetric monoidal categories or groupoids where translations are faithful, you also have a definition from Bass. Okay, so the usual properties that K2R is indeed functorial. K2 is a functor. Yeah, from rings to abelian groups, Morita invariant, all those things hold. Then you can extend the long exact sequence. Yeah, so now we have a 9-term long exact sequence, which also consists of K2. Yeah, the sequence on the first slide. This sequence can be extended here with 3 more terms coming from K2. Exactly same agenda. However, like I will not show you any computations of this. I'll just state a couple of results that if you have a finite field, then this is 1. K2 of a finite field is 1, and K2 of rational numbers, yeah, this actually seems to be a hard result to prove, is isomorphic to Z mod 2Z, direct sum, disjoint union. I mean, disjoint union or a coproduct, you can think of it as a coproduct of P in P prime of FP cross. So Milnor's name comes into picture when we are talking about K2. The K2 that was defined by this Steinberg's short exact sequence, that is good in the sense that it completes this long exact sequence. It adds more terms to long exact sequence, which has the possibility of further extension, which is what Quillen did. However, Milnor said that you can also define K2 in a different way, slightly different way, which is useful in number theory, but only for fields. So Milnor's K theory, Milnor's K2 is quite famous in number theory, but we are not going to do that. It involves some tensor algebras, its definition also. We are not going to look at that. We'll just like end our study of K2 over here. just a quick review of K2. Any questions? Okay, fine. So let us start with the second topic now. So there are many properties of K groups. Yeah, so they can be nicely defined. For like one thing is that now that we have defined K1 and K2, you also can define some products. Some products from KR tensor KS to KR plus S whenever R and S are small enough for now. Yeah, so you also have we have a graded structure for K groups. I'm sure you will see more about this. So like KNR tensor KMR to KM plus NR. You'll see more about this in higher K theory. Yeah, I'm not going to say anything more. But in particular, you have an action of K0 on K1, K0 on K, then K1 tensor K1 maps to K2 and so on. So there is one more property which I would like to state. So this is the first one. Then there is a Mayer-Vittoris sequence. So those of you who have studied homology in topology, so Mayer-Vittoris sequence is something which is common there. So this is also satisfied by the K groups. So I will show you what it is. So if R to S to R mod I to S mod I with this map F and this map the corresponding F bar is a Milnor square. So if it is a Milnor square, which means this is a pullback. In other words, I mean, this is a pullback and I is the ideal of R that is mapped. Yeah, I mean, I should say where I is an ideal of R that is mapped isomorphically to an ideal of S. Okay. Then we have this 6-term long exact sequence which will be extended later. If your like a instructor wishes to do that. So K1S direct sum K1 of R mod I to K1 of S mod I. Well, this map is the diagonal. Yeah, obviously R has maps to S and to R mod I. And this map is plus minus. Just to make it a chain complex, you need this. And then the same thing. So K0 of R. Yeah, this is always a connecting map. Then K0 of R to K0 of S. Direct sum K0 of R mod I. This is again the diagonal map to K0 of S mod I. So there is another long exact sequence which was due to be extended on either side. Right, so this is Mayer-Vittoris sequence. So K theory behaves a lot like homology theory. So this is one more proof of that. So in particular, I mean, when is this useful? So this is useful in the when you have some conductor squares. So for example, useful for R integral domains and S is its integral closure in its field of fractions. So in number theory, this is quite useful. To compute K groups. Okay, then yes, so now perhaps I should not say anything on this particular slide. I should move a bit forward. Right. So K0 and K1. So when Quillen took up this problem, then he looked at the category of finitely generated projective modules in two different ways. So Quillen has a plus construction, which is a direct construction of a topological space, which satisfies certain properties like whose first fundamental group is isomorphic to K1, second fundamental group is isomorphic to K2. So he rigged that topological space. That is the main contribution of Quillen, that he could construct this plus space. Then he also looked at the category of projective modules as a symmetric monadal category, which we have already seen that proj are with respect to direct sum and zero module, the class of zero modules. That I mean, this is a symmetric monadal groupoid with faithful translations. So that idea of Bass was already around. So he defined something called S inverse S construction, where S is a symmetric monadal groupoid. So it is the categorification of the group completion idea. So those two were good, but he also defined K theory for something called exact categories. So for exact categories, he defined the Q construction. So, and later on, he proved that all these three constructions actually give you the same result ultimately. So that is Quillen's theorem A. Okay. So what are exact categories? Well, I hope that all of you know what abelian categories are. So let A be an abelian category. I mean, quickly to recall the definition, abelian category is an additive category. I mean, it has direct sums, it has the kernels, co-kernels, and every mono is a kernel, every epi is a co-kernel. Of course, I mean, the home sets have enrichment from abelian groups and compositions are bilinear. So this is the definition of an abelian category. Let E be a skeletally small full subcategory of A that is closed under extensions. Yeah, closed under extension means that whenever you have, I mean, it's an abelian category. So whenever you have this A1, A2, 0, a short exact sequence, and whenever these belong to E, these two objects belong to E, then this belongs to E. So this is the extension. Yeah, as we just saw the definition, extension of A2 by A1, then this also belongs to E. All right. So then EA is called an exact category. So exact category, like for now, we are going to define it with respect to an embedding inside an abelian category. There are other definitions. You define it to be an additive category with a specified set of exact sequences, but we are not going to follow that for now. So this is an exact category. So some example. So the notion of, so why exact category? Because the notion of SES, short exact sequences, can be borrowed from A. So we have a specified collection of short exact sequences, like all such A1, A2, where A1, A2, and A, all of them belong to the to E. Then this is an exact category. So naturally, like for some examples of this, one motivating example was, of course, Proj-R. Can anybody tell me which abelian category this sits inside? Proj-R?
R mod.
But be careful, mod R.
Right.
We are talking about, yeah. So mod R, yes. So mod R is correct. Then another category which will be, which is also interesting. So the finitely generated modules over a ring R, they also form an exact category. Same thing, it's sitting inside mod R. Then this further contains a smaller subcategory. This will be of particular interest to us today, that is mod FPR. So FPR means finite type projective resolution. So let me define it. So M belongs to mod FPR R if there exists a finite type projective resolution. Now the phrase finite type has two different things. First of all, there is a finite projective resolution, and all the projective modules in its resolution are finitely generated. So both these things are combined. So basically there is a short exact sequence which looks like this. Okay, so this is the augmentation map, but where there exists this such that Pj are in Proj-R. So finite type projective resolution. So for example, I don't want to say for example, but I think maybe I should continue with more definitions. Then of course, free modules, they are also closed under extensions. Free finitely generated modules, of course, we want it to be a skeletally small category, so that's why it's important to just consider finitely generated. Then another class of such categories comes from topological K-theory, where people study vect fx. So the category of vector bundles, f vector bundles, real or complex, usually over X. I'm not going to define what vector bundles are, but you can see that topological K-theory is also being studied simultaneously when we are doing this. Vector bundles over a topological space. Then, well, yes, for now, let's settle with these many examples. Or we can also say, oh sorry, I forgot. So coherent sheaves. With over X. Yeah, when you study K theory of schemes, then this particular example will be important. So this also carries the structure of an exact category. It is slightly larger than this vect K when X is an algebraic variety. Yes.
These last two examples, in which abelian category they sit in?
Okay. I haven't thought about it. Perhaps, I mean, this coherent sheaves, I can tell you it sits inside the category of all pre-sheaves, which is definitely abelian. It's a Grothendieck abelian category. And I think this one will also sit inside the same
Right,
thing.
you can identify them with
Yeah.
some sort of sheaves, I think, right?
Yeah.
Okay.
Okay. So, I mean, these exact categories as well as symmetric monadal categories, like all of these examples also have a symmetric monadal structure. So they are, OX modules will also work. Yes. Thanks, Vijul. Yes. So these carry symmetric monadal structure as well as exact structure. So you can see why K theory is horizontal, which is my basic expectation. Your takeaway should be takeaway from all the K theory series that K theory is a horizontal subject. It doesn't grow vertically. Okay, so given all these examples, one particular class of rings which is of interest to us today, that is the class of regular rings. So say that R is regular. I mean, here we are talking about right regular. If R is right Noetherian, and mod FG R is equal to mod FPR R. So every finitely generated module has a finite type projective resolution. No, Aritra, so vect X is itself not abelian. That is not an issue because, see, what is our definition? E comma A is an exact category. We never expect E to be abelian. Yeah, E is just sitting inside an abelian category and it just borrows its structure of exact sequences from that parent ambient abelian category. That's all.
Okay, thanks.
Yeah. Okay, so a ring is right regular if it is right Noetherian, and every finitely generated right module has a finite type projective resolution. So in particular, if you have a finite right global dimension, if the ring is right Noetherian and has finite right global dimension, then it is a right regular. So for example, PIDs and DDs, Dedekind domains. Yeah, they are right regular. I mean, these are commutative, so just regular. And group rings are never regular. But these right regular rings have played quite an important role in the study of K theory. So we will see what to do with them. And I mean, yeah, in general, like Noetherian rings with finite right global dimension in particular. Yeah, I mean, this is also one thing. So now that we have seen some examples of these categories, exact categories, we should also know how to define this lower K theory for exact categories. So let us do that. So K0 of E. Yeah, so notice that I'm not using E comma A, and the reason will be clear very soon. So K0 of E has as its generator. So let me define that. Let E0 be a set of objects such that every object of E is isomorphic to an object in E0. So basically, I'm choosing some skeleton of E. Then consider the free abelian group on generators on these classes, yeah, for P in E0, modulo these two types of relations. This should not come, the first one should not come as a surprise to you if P is isomorphic to P prime. Yeah, two isomorphic objects should get the same class. And secondly, the class of P equals class of P1 plus class of P2 whenever 1 P1 P P2 0 P1 P P2 0 is an SES in E. So we have to simply take a free abelian group and quotient out by these relations. No pairs necessary. Right. So earlier, what we did for symmetric monodal categories, we took the isomorphism classes, then we defined pairs modulo some equivalence relation, the stable equivalence relation. Here we don't need any stable equivalence relation. Yeah, just this particular set of relations is sufficient. Right. So this will give you K0E. So this one, like at this point, I should say something about one very interesting problem in mathematics. So that has to do with Hilbert's third problem. You can say that it was the beginning of K theory. So Hilbert asked if two polytopes in n-dimensional space with equal volume, whether they are cut and paste equivalent or scissors congruent, which means you take two, let's consider the two-dimensional situation. If two polygons have the same area, then can you cut first polygon into finitely many pieces and join them again to get another polygon, the other polygon? And the answer in 2 dimensions is yes. Area is the only invariant. Whereas in 3 dimensions, Max Dane immediately settled this problem, Hilbert's third problem, in the negative in 1902 itself, that volume alone is not sufficient in dimension 3. You need something more. Yeah, I mean, the one tetrahedron of volume 1 cannot be cut into finitely many pieces, and if you put those pieces together, you can never get a unit volume cube. Yeah, so unit volume tetrahedron and unit volume cube, they are in different classes, which means their classes in the K group are different, and this is exactly cut and paste relation. The P1 and P2, yeah, I mean, we are oversimplifying essentially. The middle P can be put in different ways. Yeah, that's why the theory of extension groups, X1, comes into picture. You can put various different groups in between P. There are multiple extensions, but K theory actually tries to identify all of them. So whatever extension, we just need that it is an extension of the of P2 by P1, then its class will be the same. Yeah, so this is also known as scissors congruence. So this is the congruence relation, and the second one is the scissors relation. It's like you are breaking a module into two halves. Okay, so K0 of E will actually show what scissors congruence is. And then the theorem obviously is that, well, K0 of a ring is isomorphic to K0 of Projar, thought of as an exact category. So recall that Projar itself is not abelian. It's just additive. It's not necessarily abelian. But these two definitions will give you the same result ultimately. Okay, so any questions? Fine. So now we can move on to defining what is K1E. So again, free abelian group. On generators which are P comma alpha, well, this also shouldn't come as a surprise to you, where P is in E0 and alpha is an automorphism of P. So we are again, they can't be very different. They again have to resort to automorphisms in some or other way. Modulo the relations that if you take P alpha multiplied by P beta, I mean, I can also write it additively if you wish. That is same as P alpha beta. So you can combine, compose them and you will get addition. So this is one type of relation. And whenever you have a short exact sequence of automorphisms, and so P alpha equal to P1 alpha 1, the class of P1 alpha 1 plus the class of P2 alpha 2, where this one is a short exact sequence. So P1, P, P2, 0, 0, P1, P, P2, 0, and here is alpha 1, here is alpha, and here is alpha 2. Commutes. So it's like this alpha is the extension of the automorphism alpha 2 by alpha 1. Yeah, so whenever this happens, then you identify it. And this presentation is very nice because it looks very much like K0 of E. Yeah, again, the theorem would say that K1 of E of a ring R is isomorphic to K1 of Projar. Now, yeah, I mean, I made a point earlier that observe that I'm not talking about E comma A, because it doesn't matter which ambient abelian category you are working on in. The exact structure of E is inherent, it's inbuilt, and nowhere are we using references to any A. Yeah, the ambient category A. So therefore it is K0 of E and K1 of E. Okay, so like the German word Klasse, which stands for, I mean, the letter K in K theory. So G theory can also be done. And well, I would like to believe that G theory is named after Grothendieck. So G theory, the groups Gj of R are defined to be Kjs of the category of finitely generated modules. And these are in particular interesting for R Noetherian. Yeah. So this is G theory. You can also study a slightly larger category of finitely generated modules, and then that becomes G theory. There are many results about G theory as well, but it is like a branch of K theory. All right. Any questions again? Okay, so I'm just going to start writing lots of theorems now. Yeah, the proofs of these results are very long, but like I shouldn't end the session on lower K theory without talking about these important results. So the first one is Grothendieck's the visage. Yeah, so let A be an abelian category with a set of simple objects up to isomorphism, and let AFL be the full subcategory of finite length objects. So the finite length is defined using Jordan-Holder theorem. Perhaps you have seen it in group theory, which you can extend it here easily. So finite length objects. Then AFL becomes an exact category. Yeah, okay, I mean then AFL is an exact category. And K0 of AFL is simply the free abelian group on isoclasses of simples, and K1 of AFL is the direct sum of the automorphisms of simples, the abelianization of the automorphism of simple groups. So this is if you are studying K theory for the first time, yeah, then perhaps this is the first category that you should compute. Yeah, very easy to see result. The proof is easy. Like the spread of the category doesn't really matter as long as you have full control over simples. So this is Grothendieck's the visage. Then well, I have never said this thing explicitly, but perhaps I should say something today. So there is a Swan theorem. It says that the category of vector bundles, yeah, I mean, this is a connection, yeah, this is a beautiful connection between topological K theory and algebraic K theory. So and I'm just going to state its simplest possible version. If X is compact Hausdorff, then the category of vector bundles with complex values, I mean complex vector bundles over X is equivalent to the category of finitely generated projective modules over the ring of continuous complex valued functions on X. And as a consequence, and therefore, Kj of X topological K theory is same as the algebraic K theory of the ring of continuous functions. Well, you can also replace C with R in this case. I mean, for now, we should just say J is equal to 0 and 1 because we haven't defined K2 of an exact category. So this is the beautiful connection between topological and algebraic K theory, which I'm sure you will see in detail later on. But this particular connection is quite important for us to understand something. Yeah. So our next point is Stone-Weierstrass theorem. Can anybody remind me what it is? I'm sure everybody has studied it in first analysis course, real analysis course. Anyone? Okay, so all of you are algebraists. Don't want to say anything about, I don't remember analysis right now, but it's okay. Stone-Weierstrass theorem says that the polynomial ring is dense in the ring of continuous functions. Polynomials are dense in the ring of continuous functions. Okay, so once we know this density, so what is algebraic homotopy? So this is, the topological homotopy. So topological K theory is a homotopy invariant. Okay? So the ring, I mean, of course, I want to say this, that X cross the interval 0, 1 is homotopy equivalent to X, the cylinder. Correct? So therefore, correspondingly, we should also have the ring of continuous functions on the cylinder with complex values is, I mean, this should be similar in some sense to, I mean, sorry, I don't want, I'll just use this to the ring of continuous functions on X. Yeah, this is not explicit, but as a consequence, what you get is that Kj of the cylinder space is isomorphic to Kj of X. So this is the topological, like homotopy invariance of topological K theory. Now, for the corresponding algebraic homotopy, what do we say? That the ring of continuous functions, so let me call this particular ring R. Then if I take the ring of polynomials, then this is dense inside the ring of continuous functions on the cylinder. Via simply this specialization map. I mean, T maps to some, T specializes to some element in the interval 0, 1. This is a consequence of Stone-Weierstrass. And therefore, we should expect, should expect, at least in nice scenarios, that the map, so you take this Cx cross 0, 1 to C, and then you can simply project onto Cxc. Yeah, so there is a map down to R again. So Kj of RT is actually isomorphic to Kj of R for nice rings. Well, actually it does happen. Yeah, this actually does happen. And then word nice stands for regular. And this is a theorem of Grothendieck. Okay, so this is Grothendieck's theorem. That Kj of Rt is isomorphic to Kj of R for regular rings. Yeah, that's why we studied regularity. Well, here I should say a few lines about how we are doing it. If the ring R is regular, then in particular it is Noetherian. And the ring of polynomials over a Noetherian ring is also Noetherian. This is Hilbert basis theorem. Yeah, so that is being used. And moreover, if the ring is regular, then Hilbert's syzygy theorem says that RT is also regular. So you use Hilbert basis theorem and Hilbert syzygy theorem in the proof of this. So this algebraic homotopy also works in the case of nice regular rings. Yeah, so RT is actually thought of as the cylinder construction on R, and it is homotopy equivalent to R. Well, yeah. In fact, we can also say that if R has a global dimension n, right global dimension n, then the right global dimension of RT is at most n plus 1. And that also happens because of this free resolution of R as an RT module. So you can check this. This is a split exact sequence. So T mapping to 0 to 0. This is split. This splits by sending. This is simply the inclusion. So this is a split exact sequence. Well, now to take this a bit further, we will also talk about the algebraic topological desuspension. I'm still not clear. If somebody from audience is familiar with so much algebraic topology, then why is X cross S1 called a desuspension? At least Rosenberg states that. So this is for, sorry, I should not say C here. So Kj of X cross S1 comma C actually splits because of Bott periodicity. This is Kj of X. Oh, sorry, what am I saying? Well, I did not introduce this Ku, but this is the complex one. Yeah, let's say this is the complex one. So Kj of X direct sum Kj minus 1 of X. So there is this result in algebraic in topological K theory, that Kj of this X cross S1 splits in terms of two K groups. So what is the difference between 0, 1 and S1? That every element in S1 is invertible. So therefore, the corresponding algebraic desuspension should say something about the corresponding localization. So RTT inverse and R. So RTT inverse once again is a dense subring of the ring of continuous complex valued functions on X cross S1. Okay, so RTT inverse, its Kj should be isomorphic to Kj of R, direct sum kj of kj minus 1 of R. So this also holds for regular rings. And this is a result due to Bass-Heller and Swan. So this is known as Bass-Heller-Swan theorem. For regular rings, you can split the kj of ring of these algebraic desuspension into two k groups. But then you can ask what happens in general. Oh, well, maybe I should also say there is a corresponding to this particular T, this localization of the polynomial ring, Laurent polynomial rings. You also have this split short exact sequence. Which gives you the same kind of result for so where T maps to 1 now, and this is simply inclusion. So this is also split exact. So this split exact sequence is useful in here, in the proof of this. And the split property actually gives you this direct sum. So now see what happens when I talk about K1. Yeah, for a regular ring, at least for now, for a regular ring. So if I know K1 of the ring of Laurent polynomials over R and K1 of R, then actually I also know K0 of R. So I can go one step down. Now this is the motivation for negative K theory. If I do the same thing with K0, so K0 of the ring of Laurent polynomials, K0 of R, then I will get some factor, and that factor would be K minus 1 of R. But of course, not everything is good always. This formula only works for regular rings. So what happens in general? Okay, so in general, we have to define something. So for general rings R, define nkj of R to be the co-kernel of the map from kj of R, the split inclusion, to kj of RT. Then actually Bass-Heller-Swan turns out to be this statement. So Bass-Heller-Swan, in a more general form, they also proved something for all rings, that kj of R has two more factors in general. Kj of RTT inverse is isomorphic to kj of R, direct sum kj minus 1 of R, direct sum n kj of R, direct sum n kj of R. So these two copies of nkj, they come from the embedding of RT into RTT inverse and RT inverse into RTT inverse. So, this can be used to define the negative K group. So let me see. Well, yeah. So this is how, negative K groups are defined by above isomorphism. Yeah, because you do it for 0, then you get -1, 1, you get -2, and so on, inductively. And well, this is a nice short exact sequence. I mean, this is not exactly short, but still short enough. So let me say this. So K1 of R, then K1 of RT, direct sum K1 of RT inverse. Then, so this is the delta map. Obviously, you can embed it inside both the rings and then corresponding maps. Then this is the +-1 map, K1 of RT T inverse. But the sequence, this sequence is not exact. So you further need a co-kernel of this, and that is K0 of R, and then to 0. And moreover, whatever this map is, it splits. So here it is split embedding. K0 of R splits inside this. So in general, like I will say that for defining negative K theory, I mean, whatever I wrote just now, yeah, I mean, that is known as the fundamental theorem of algebraic K theory. So here I can subtract, yeah, I mean, this 1, I can subtract 1 minus n, 1 minus n, 1 minus n, and this becomes minus n. So that's how for all negative numbers also you can define it, negative groups. And obviously, I mean, this construction is also well behaved, like it extends, yeah, so negative K groups extend the long exact sequence on first slide. Yeah, you can define. So now we have got an infinite long exact sequence for all negative K groups, K0, K1, and K2, but you don't know what to do with K3 and so on. And mainly because our intuition fails beyond K2. K0 is quite nice. K1, it's okay. I mean, we still understand its abelianization, some abelian invariant of the category. K2 is hard to imagine, like the commutator subgroups of automorphism groups and then take direct limit and why take second homology group. Yeah, the intuition starts failing at that point. Well, with some pushing forward, you can define what is K3, but that was not going to solve the problem of what all higher K groups were. Yeah, then the genius of Quillen comes into picture, and this is where I stop. So I want to say something that, I mean, this is my first time giving us such a general talk on this new subject. So please, if you have any feedback, do send it to me on this email address. Positive, negative, anything would be useful. Sorry, iitk.ac.in. I'm sure this was pretty fast. Like for those who are looking at K theory for the first time, this is just a bird's eye point of view. But I would like to get some feedback, or you can tell me orally also. But thank you all for being here for 4 weeks. And this is a lot of work even to attend. Any questions? All right. Mainak.
Sir,
Yeah, yes.
I have a very general question. So
Yes.
so you said that Quillen obtained a topological space out of a ring, and all of its monotopy groups were k groups for positive n, right? For
All of its
positive
homotopy?
k groups were k groups of that
Yes.
that ring.
Yes. Not
So
all, the first two.
Yeah, but then
like
he extended
K1
it
and
using the
K2.
same idea. Oh wait.
No, then he simply used the long exact sequence of homotopy groups. So
he
he
defined
didn't.
Kn for larger n.
Yes. So pi n. So his formula is like this. So he defines some space. Yeah, I mean, well, I'm not sure I should do this, but the K theory space is defined to be BGL plus of R, and to rig K0 like pi as pi 0, you take K0 R many copies of this. So you take so many connected components of this, and then pi n of I should say some differently. Kn of R was defined to be pi n of this K theory space for n bigger equals 0.
Right, and it agreed with the 0, 1, and 2.
Yes, it agreed with 0 because this is a connected space, and K0 you are artificially adding. If you remember what K0 is, pi 0 is, it's simply set of simply connected components.
Right.
So it generally only has a monoidal structure if it is an H space, but here in this case, because K0R is a group itself, it also gets a group structure, abelian group structure. The major work was involved in defining this BGLR plus because mostly because K1 and K2 were already in existence. So that was a lot of expectation from mathematical community. It should match for 3 terms.
Right. So my question was, is there an interpretation of negative K groups?
No, not in terms
way?
of this K space. No, not in terms of this K space, as far as I know.
Okay.
Negative K groups are just defined by this fundamental theorem of algebraic K theory. So even topological K theory is also defined using a similar construction, suspension, desuspension. Yeah. So when you see that, you'll know more. So it's simply bought periodicity. Yeah, period 2 for complex numbers, and I think it's period 8 for real. Yes. So negative K groups are easily defined. People don't study positive topological K groups. So usually it is denoted by K minus J, KO minus J or KU minus J for orthogonal or unitary, real or complex. Yes, there is something like, please share feedback link. Okay. I mean, this is not a link. This is my email address. Asif. I will still write it. Oh, sorry. I did not write it to everyone. Yes. Any kind of feedback is welcome. And any questions? More questions?
So I have a question about an
Yes.
particular example. So in representation theory of finite groups, we have the group algebra CG. So these lower K groups for this group algebra, are they well understood? Like as you said, something like these group rings are not regular. So like, do we know anything about the K groups of these CG, where G is a finite group?
Okay. So first of all, if you try to obtain literature on K theory, then except for a few books, which I already mentioned, Bass, Rosenstein, Rosenberg, or Weibel, there aren't any good references. So you actually have to skim through research papers to know these things. So I have no idea, but I would say that the group rings or group algebras, they are very difficult objects to study.
Okay,
so therefore not much is known. Even for K1 and K0, not much is known. There is an entire theory developed by Whitehead for K0,
Okay.
K1.
Okay.
Which I did not cover because we don't want to assume a lot of topological background. But
Okay.
it's a special branch of K theory where you only study group rings.
Okay. Okay. So what is that called? Like, is that
Whitehead groups.
Whitehead groups? Okay.
Yes.
Okay.
So Whitehead has done a lot of work in this direction. Yes.
Okay. Okay, sir. Thank you very much.
Okay. Yes. Mainak, we should probably stop.
Okay. So thank you, Professor, for this wonderful lecture. With this, we will end today's session, and this concludes the first section of algebraic K theory. The next section, higher algebraic K theory of rings, will start from next week, and it will be delivered by Professor Girja Shankar. You can check out the website for the link, or it will be also be shared through email if you signed up for the course. I hope you're all enjoying the series, and thanks for joining. Have a good day.